Welcome! In this session, we'll tackle an interesting problem, sum of mutated array closest to target. Together, we'll explore the problem statement, dive into potential approaches, and break down the solution step by step. Let's get started. In this problem, you are given an integer array ARR and a target integer target. Your task is to replace each element in the array with a new value, referred to as v, to create a mutated array. The goal is to make the sum of this mutated array as close as possible to the given target. However, there are some constraints to keep in mind. The value v that replaces elements in the array must be greater than or equal to 0. Additionally, for each element in the array, the mutation is performed using the formula min a_i v, meaning that each element in the array is either replaced with v or remains unchanged if it is already smaller or equal to v. Once the mutated array is formed, you need to return the value of v that minimizes the absolute difference between the sum of the mutated array and the target. If there is a tie, meaning two values of v result in the same absolute difference, you must select the smaller value of v. To understand this problem more clearly, let's consider an example. Suppose the input array is 4, 9, 3, and the target is 10. If we choose v equals 3, all elements in the array greater than 3 are replaced by 3, resulting in the mutated array 3, 3, 3. The sum of this array is 9, which has an absolute difference of 1 from the target. Now, if we pick v equals 4, the mutated array becomes 4, 4, 3, giving a sum of 11 with an absolute difference of 1 as well. Since both values of v result in the same absolute difference, we return the smaller value, which is 3. This example illustrates how to determine the optimal value of v by examining the resulting mutated array and its sum. Now, consider another example where the input array is 2, 3, 5, and the target is 10. If we choose v equals 5, all elements greater than 5 are replaced with 5, but in this case, no elements are actually changed because all the values are already less than or equal to 5. The mutated array remains 2, 3, 5, and its sum is exactly 10, which matches the target. Since we have achieved the exact target sum, the output in this case is 5. This demonstrates how the problem handles scenarios where the target is met without requiring extensive mutations. Lastly, let's look at a more complex example with a larger array. Suppose the input is 60864, 25176, 27249, 21296, 20204, and the target is 56803. If we choose v equals 11361, all elements greater than 11361 are replaced with 11361, resulting in the mutated array 11361, 11361, 11361, 11361, 11361. The sum of this array is as close as possible to the target. This example highlights how the solution must efficiently handle larger inputs and constraints. To summarize, the problem requires finding the optimal value of v to minimize the difference between the mutated array's sum and the target, while adhering to the rules about how elements are replaced. To solve this problem, let's start by considering the brute force approach. The idea here is straightforward: we replace each element in the array with values ranging from 0 up to the maximum element in the array or the target value, whichever is smaller. For each combination of mutations, we compute the sum of the array and track the mutation that brings us closest to the target. This guarantees that we'll find the optimal solution, but the drawback lies in its inefficiency. The time complexity can grow significantly, as we would need to evaluate O and max (rr) combinations, where n is the size of the array and max (rr) is the largest value in it. This makes the approach impractical for larger arrays or large values of max (rr), especially given the constraints where the array length can go up to 10,000. While exhaustive, it's simply not feasible for real-world cases within these limits. Instead of brute force, we can use a binary search approach to make the process much more efficient. The first step is to sort the array, which helps us reason about the effects of mutations systematically. Then, we define a helper function that computes the sum of the array for any given mutation value. The goal is to use binary search to zero in on the mutation value that minimizes the absolute difference between the mutated sum and the target. The search range is set between 0 and the largest value in the array, max (rr). At each binary search step, we calculate the sum for the midpoint of the range, compare it to the target, and adjust the range accordingly. The reason this works is that the relationship between the mutation value and the array sum is monotonic. Mutating all elements to a single value or leaving some unchanged creates a predictable progression. This property makes binary search both effective and efficient. The time complexity here is O, n log, max, r, which is a significant improvement over brute force, and the space complexity is O, 1, aside from the input array. However, care must be taken during implementation to handle edge cases, such as ties between mutation values. To further optimize the binary search approach, we can use a prefix sum array. This helps us compute the mutated sums more efficiently by avoiding repeated calculations for the unmutated parts of the array. Essentially, the prefix sum allows us to split the array into two parts, the elements affected by the mutation and those that remain unchanged. This optimization slightly reduces the constant factor in the time complexity, keeping the binary search at O, n log, max, r, while adding an O, n, step for computing the prefix sum. However, it does introduce an additional memory overhead of O, n, to store the prefix sums. This trade-off can be beneficial for some cases but may not always result in a noticeable runtime improvement. Ultimately, while the prefix sum approach is faster in theory, the added complexity and memory usage must be weighed carefully. The binary search approach is the best choice for this problem because it strikes the right balance between efficiency, simplicity, and scalability. Compared to brute force, it avoids the combinatorial explosion of possibilities, making it feasible for larger arrays. While the prefix sum optimization adds a slight speed advantage, the additional memory usage and complexity don't offer enough of a benefit in most scenarios. The binary search method handles arrays with up to 10,000 elements and values up to 10,000 efficiently, staying well within the problem's constraints. The monotonic relationship between mutation values and the array sum is the key insight that enables this approach, and sorting the array further simplifies the implementation. All things considered, binary search is the most practical and effective strategy for solving this problem, offering the best balance of runtime efficiency and ease of implementation. The problem we're solving here is to modify an array such that the sum of its elements comes as close as possible to a given target value. The key constraint is that each element in the array can be replaced with any value between 0 and the maximum value present in the original array. This makes it a combinatorial optimization problem since we need to explore various possible configurations of the array to find the one that minimizes the difference from the target. The brute force approach to solve this problem begins by initializing the input values, the array, the target, and the maximum value in the array. Then, we generate all possible combinations of the array by iterating through replacements for each element, ranging from 0 to the maximum value. With a nested loop structure, we end up generating a total of max_val raised to the power of n combinations, where n is the size of the array. For each of these combinations, the next step is to calculate their sum, which will later be compared to the target value. After generating all possible combinations and computing their sums, the next step is to track the combination that has the closest sum to the target. This is done by maintaining a variable called closest_sum, which keeps track of the smallest absolute difference between a combination sum and the target. For every combination, we calculate the absolute difference and update closest_sum whenever a better result is found. Once all combinations are evaluated, the array configuration that produced this closest_sum, along with the sum itself, is returned as the result. For example, if the input array is 1, 2, 3, and the target is 4, the maximum value in the array is 3. By replacing each element with values between 0 and 3, we generate 4 cubed or 64 different combinations. For each combination, we compute its sum and compare it to the target, updating closest_sum whenever a smaller difference is found. This ensures that the final result is the array configuration that gets as close as possible to the target sum. The brute force approach, while straightforward, has significant limitations. First, its exponential complexity makes it computationally expensive. The time complexity is O, max_val n, meaning that even small increases in the size of the array or the maximum value can lead to a massive increase in the number of combinations. Another drawback is that this approach does not use any optimization techniques, such as pruning combinations that are unlikely to improve the result. On the positive side, brute force guarantees finding the optimal solution because it explores every possible configuration. To implement this, we use basic data structures like arrays to hold the current combination being tested. Variables like closest_sum track the best result we've seen so far, and best_combination stores the corresponding array configuration. However, due to its inefficiency, this method is impractical for larger inputs. To address the inefficiencies of the brute force approach, several optimizations can be introduced. One way is to implement early termination. If we find a combination that matches the target exactly, we can stop further computation immediately. Another optimization is to pre-compute bounds based on the maximum value, which helps in pruning unnecessary combinations. A more sophisticated alternative is to use dynamic programming. This technique builds subsets iteratively, reducing the solution space significantly and avoiding the need to evaluate all combinations. When analyzing complexity, the brute force time complexity remains O, max_val caret n, and the space complexity is O, n, due to the storage requirements for the array being modified. However, the exponential growth in combinations makes this approach infeasible for large input sizes. These limitations highlight the need for smarter strategies that leverage the structure of the problem to improve efficiency. In conclusion, while the brute force approach provides a clear and straightforward solution, its exponential computational cost makes it impractical for real-world applications with larger inputs. Despite its inefficiency, it guarantees the optimal result because it evaluates every possible array configuration. However, a high computational demand emphasizes the importance of exploring optimizations, such as early termination or dynamic programming, to make the solution more scalable. Ultimately, the brute force method serves as a foundational approach, but for larger or more complex inputs, adopting more efficient techniques is essential. Here, we are implementing the solution to find a value such that the sum of the mutated array is closest to the target. First, we define a helper function, calculate_sum, which calculates the sum of the array after applying the mutation. In this mutation, each element of the array is replaced by the smaller value between the element itself and the given value. This allows us to test sums for different mutation values easily. Next, we sort the array, which simplifies the process of determining the closest sum. Then, we initialize the bounds for binary search with left set to 0 and right set to the maximum value in the array. We also prepare two variables, closest_sum to track the closest sum we find during the process and best_value to store the corresponding mutation value. Now, we set up the binary search loop. While the left boundary is less than or equal to right, we calculate the midpoint, mid, and use it as the mutation value to compute the current sum using the calculate_sum helper. If this current sum is closer to the target than the previously stored closest_sum, or if it is equally close but mid is smaller than the current best_value, we update both closest_sum and best_value to reflect this better result. Finally, based on whether the current sum is less than the target, we adjust the binary search bounds to continue narrowing down the potential values. If the current sum is less than the target, we shift the left boundary of the binary search to mid +1, as this indicates that we need a larger value to get closer to the target. Otherwise, we move the right boundary to mid 1, since the current sum is greater than or equal to the target, meaning we need a smaller value. Once the loop concludes, we return the best_value that we identified during the process. This value represents the mutation value that leads to the sum closest to the target. This binary search approach ensures an efficient solution, as it reduces the search space logarithmically while maintaining accuracy in finding the optimal mutation value. Here, we start by importing the necessary Java utilities and defining the solution class. The main function of interest is findBestValue, which takes an array ARR and a target value as inputs. Inside this function, there's a helper method called calculateSum. This method takes a single value as an argument and calculates the sum of the array after mutating its elements. Specifically, each element in the array is replaced with the smaller of itself and the given value, and the resulting values are summed up. This helper method is essential for evaluating potential mutations efficiently during our search. Next, we sort the input array to simplify our calculations later, particularly when determining bounds for our binary search. After sorting, we initialize two variables, left and right, which represent the bounds for our binary search. The left starts at 0, and the right is set to the largest value in the array. We also declare two variables, closest sum and best value. These will help us keep track of the closest sum to the target and the corresponding value that produces this sum. Finally, we set up a binary search loop where we continuously narrow down the search range to find the optimal value. Within the binary search loop, we calculate the midpoint, mid, and use the calculate sum helper method to compute the sum of the array when all elements greater than mid are replaced by mid. We then check if this current sum is closer to the target than our previously recorded closest sum. If it is, or if it's equally close but the current value of mid is smaller, we update both closest sum and best value to reflect this new optimal value. The next step is to adjust the binary search bounds. If the current sum is less than the target, it means we need a higher mutation value to get closer to the target, so we move the left bound up. Conversely, if the current sum is greater than the target, we decrease the right bound to lower the mutation value. Once the loop completes, the binary search will have identified the value that minimizes the difference between the mutated sum and the target. Finally, we return this optimal value, best value, as the result. In this problem, we are tasked with finding a value called best_value that modifies an array such that the sum of this mutated array is as close as possible to a target value. The modification involves replacing any element in the array greater than best_value with best_value. If two values result in the same difference from the target, we choose the smaller best_value. To solve this efficiently, we use binary search. For example, with the array 4, 9, 3, and a target of 10, we first sort the array to 3, 4, 9. We then initialize our binary search with bounds left as 0 and right as the maximum value in the array, which is 9. We also track variables closest_sum to store the closest sum we find and best_value to store the corresponding value. Let's explore how this process unfolds step by step. The binary search begins by calculating the midpoint of the current bounds. In the first iteration, the midpoint is 4. We replace all elements in the array greater than 4 with 4, resulting in the mutated array 3, 4, 4. The sum of this array is 11. And the difference from the target is 1. Since this is the smallest difference we've encountered so far, we update closest_sum to 11 and best_value to 4. However, because the sum 11 is greater than the target 10, we adjust our search range by setting the right boundary to mid 1, which is 3. In the second iteration, the midpoint becomes 1. Mutating the array with 1 results in 1, 1, 1, with a sum of 3. The difference from the target is 7, which is worse than our current closest difference of 1, so no updates are made. Since the sum 3 is less than the target, we move the left boundary to mid plus 1, which becomes 2. In the third iteration, the midpoint is now 2. Mutating the array with 2 gives 2, 2, 2, with a sum of 6. The difference from the target is 4, which is still worse than the current closest difference of 1. Therefore, we make no updates. Since the sum 6 is less than the target, we adjust the left boundary to mid plus 1, which becomes 3. In the fourth and final iteration, the midpoint is 3. Mutating the array with 3 results in 3, 3, 3, with a sum of 9. The difference from the target is 1, which matches our current closest difference. However, since the sum 9 is closer to the target than previous sums, we update closest_sum to 9 and best_value to 3. As the sum 9 is less than the target, we move the left boundary to mid plus 1, which becomes 4. At this point, the left boundary exceeds the right boundary, so we terminate the binary search. The final value of best_value for this example is 4. Now let's look at a second example with the array 2, 3, 5, and a target of 11. We start by sorting the array, which remains 2, 3, 5. The binary search bounds are initialized as left equals 0 and right equals 5, the maximum value in the array. We set closest_sum to infinity and best_value to 0. In the first iteration, the midpoint is 2. Mutating the array with 2 results in 2, 2, 2, with a sum of 6. The difference from the target is 5, which is better than infinity. We update closest_sum to 6 and best_value to 2. Since the sum 6 is less than the target, we adjust the left boundary to mid plus 1, which becomes 3. In the second iteration, the midpoint becomes 4. Mutating the array with 4 gives 2, 3, 4, with a sum of 9. The difference from the target is 2, which is better than the current closest difference of 5. We update closest underscore sum to 9 and best underscore value to 4. Since the sum 9 is still less than the target, we move the left boundary to mid plus 1, which becomes 5. In the third iteration, the midpoint is 5. Mutating the array with 5 results in 2, 3, 5, with a sum of 10. The difference from the target is 1, which is the smallest difference we've seen so far. We update closest underscore sum to 10 and best underscore value to 5. Since the sum 10 is less than the target, we move the left boundary to mid plus 1, which becomes 6. Now left exceeds right, so we terminate the binary search and finalize best underscore value as 5. To summarize, for the first example with the array 4, 9, 3, and a target of 10, the output is 4. For the second example with the array 2, 3, 5, and a target of 11, the output is 5. These results demonstrate how binary search efficiently determines the value that minimizes the difference between the mutated array sum and the target. To analyze the time complexity of this solution, we begin by examining the key operations performed by the algorithm. First, we have the sorting of the array. Sorting an array of size n requires O, an asterisk log, n, time, as this is the standard complexity for efficient sorting algorithms like merge sort or quicksort. Next, we use binary search to find the optimal value. The binary search operates on the range from 0 to the maximum value in the array, which we denote as m. Since binary search reduces the search space by half in each iteration, the number of iterations is proportional to log em. Finally, within each iteration of the binary search, we calculate the sum of the array using the helper function calculate_sum. This function traverses the entire array once, replacing values greater than the current midpoint with the midpoint and summing the results. This operation takes O, n, time. Therefore, when we combine these operations, the dominant components of the time complexity are sorting at O, n asterisk log, n, the log em, iterations of binary search, and the O, n, sum calculation per iteration. Together, these give us an overall time complexity that we'll refine further in the next steps. Now, since the sum calculation is performed in each iteration of the binary search, the total time complexity for this part becomes O, n asterisk log em. Combining this with the sorting step, we get a total time complexity of O, n asterisk log, n, plus n asterisk log, m. This can be further simplified to O, n asterisk, log, n, plus log, m. Moving on to space complexity, the primary contributor is the sorting step, which typically requires O, n, additional space for temporary storage during the sorting process. The binary search and the helper function, on the other hand, do not use significant additional memory, as they rely on a few variables such as left, right, and mid, which require only O1 space. Since there are no recursive calls or additional data structures involved, the overall space complexity is determined by the sorting step, resulting in O(n). This sufficient use of space is a notable advantage of the solution. When we compare this optimized approach to a brute force method, the improvements in efficiency become clear. A naive approach would involve iterating through all possible values from 0 to the maximum value in the array, denoted as m, and calculating the sum for each value to find the closest sum to the target. This brute force method would have a time complexity of O, n asterisk m, as we would perform the sum calculation, which takes O, n, for all m values. By contrast, the optimized solution uses binary search to reduce the number of iterations to log m, resulting in a time complexity of O, n asterisk log, m, for this part. Additionally, the optimized solution includes a sorting step, which contributes O, n asterisk log, n, to the overall complexity. This sorting step is essential for enabling the binary search method, as it allows us to efficiently determine the range of possible values. Overall, the optimized solution is significantly more efficient than the brute force approach, especially for cases where m is large. To understand the performance of the solution in different scenarios, let's analyze the best, worst, and average cases. In the best case, the binary search converges quickly, and the target value is found early in the search space. However, since the sorting step still dominates, the best case time complexity remains O, n asterisk log, n. In the worst case, the binary search explores the entire range from 0 to the maximum value in the array, requiring log m iterations. Combined with the sorting step, the time complexity remains O n asterisk log n plus log m. For the average case, the behavior is similar to the worst case because the binary search and some calculation are performed for most values within the search space. To mathematically verify this complexity, consider that sorting takes O n asterisk log n due to dividing the array into log n levels and processing all elements at each level. Binary search requires O log em iterations as the range is halved in each step, and the sum calculation within each iteration takes O n. Combining these, the dominant factors are sorting for small m and binary search for large M, leading to an overall complexity of O n asterisk log n plus log am. In this section, we'll look at some common mistakes that can trip you up when solving this problem. First, not accounting for edge cases is a frequent issue. For example, what happens if the array is empty or contains only one element? These scenarios can lead to runtime errors if not handled explicitly. Next, many solutions fail because they ignore constraints on values. If the problem specifies that all numbers are non-negative or that the array size is capped at 10,000, you need to incorporate these constraints into your approach to ensure correctness and efficiency. Another common pitfall is overusing brute force. While brute force may feel intuitive, it often results in exponential time complexity, which becomes impractical for large input sizes. Optimization is key here. Additionally, failing to validate intermediate results can cause problems. For instance, when you're performing incremental computations, it's important to check whether each step is bringing you closer to the target or staying within bounds. Lastly, hard-coding values, like a specific target or array size, should be avoided. This practice makes your solution less adaptable to different test cases. Instead, rely on variables or constants to handle diverse inputs effectively. Now, let's explore some insights that can help you during interviews. Recognizing patterns in array-based problems is a critical skill. Techniques like binary search, prefix sums, and dynamic programming frequently appear in such problems, so being able to identify when they're applicable can significantly improve your efficiency. It's also important to optimize early. While it's fine to start with a brute force approach, you should quickly identify redundant computations and think about how to eliminate them. This not only improves performance but also shows the interviewer that you understand the problem deeply. Additionally, explaining the trade-offs between different approaches demonstrates clarity of thought. For example, you might mention that a greedy solution is faster but less flexible, whereas dynamic programming might handle a broader range of cases but uses more memory. Don't forget to ask clarifying questions at the beginning of the problem. This practice helps you identify edge cases and constraints, such as whether the array can contain negative numbers or what to return if no solution exists. Lastly, always test your solution with a variety of inputs. Edge cases like arrays with all identical elements, empty arrays, or very large inputs can reveal potential flaws in your implementation. To broaden your understanding, let's look at some related problems that share similar concepts. The two-sum problem, LeetCode 1, is a classic example where you need to find two numbers in an array that add up to a specific target. Hash maps are often used here to optimize the solution. Then, there's three-sum, LeetCode 15, which extends this idea to find triplets instead of pairs. This problem typically involves sorting and two-pointer techniques to reduce complexity. Another variation is closest sum, LeetCode 16, where the goal is to find three numbers whose sum is closest to the target. This problem tests your ability to optimize while considering edge cases. Lastly, subarray sum equals k, LeetCode 560, challenges you to count the number of subarrays that sum to a given value. Efficient solutions to this problem often rely on prefix sums combined with hash maps to keep the runtime manageable. Exploring these problems can help you build a strong foundation and recognize patterns that apply to a wide variety of scenarios. Finally, let's examine some alternative approaches and the trade-offs they involve. One effective method is sorting the array and using two pointers to find sums closest to the target. This approach simplifies the problem and reduces the need for nested loops, though it does require O n log n time due to the sorting step. Another option is binary search, where you search for elements that complement the current one to meet the target. This can improve runtime compared to brute force but requires careful handling of edge cases. Dynamic programming is another powerful tool, especially for problems involving subsets or combinations. By storing intermediate results, you can avoid redundant computations, though this often comes at the cost of higher space complexity. Finally, greedy algorithms can be useful for making locally optimal choices, such as picking the smallest or largest numbers first. However, these approaches may not always yield the globally optimal solution, so it's important to validate their effectiveness based on the problem's specific requirements. Each of these strategies has its strengths and weaknesses, so choosing the right one depends on the problem constraints and your familiarity with the techniques. Great job! To summarize, we reviewed the problem, sum of mutated array closest to target, discussed the brute force approach, and emphasized the importance of optimization. Keep practicing to strengthen your problem-solving skills. Thanks for watching, and I hope to see you in the next session. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!